So, hello everyone. Let us start. Okay, fine. Okay, so let's start the assignment. Samples for week 5. Such is an so this week will be more of SSPSC, DSPSC, PSBSC, all this sort of analog communication type of thing. This tutorial is more of this type of communication engineering skills. So let us start the first question. The first question of the today's first sample question, I must say, not the exact assignment questions. These are first question is ISSBSC and a VSBSC. These two modulation we already know from the lectures. So we have to comment true or false. And I am making the statement here that both the modulations can be used for voice and video communications. And you have to comment whether it is true or it is false. So the answer is everybody knows it, that the SSB-SC signal is used only for voice communication. And this is the most efficient. However, this cannot be used for video transmission due to a large video bandwidth. We just cannot take the only single sideband. So SSB-SC signal is only for this is in terms of bandwidth, not anything other. Not according to performance, I will not say, but in terms of bandwidth parameter, SSB-SC is the most efficient. So, but it cannot be used for video. So, the correct answer is only not the correct answer here. VSB-SC is the only modulation scheme here, and with DSB-SC also, DSB or DSB-SC. These two schemes and VSB-SC. These can be used for video also. So the question says both the modulations. So both the modulations cannot be used for video and voice communication. So the option is false, because SSB-SC can only be used for voice communication. Okay. Next one. Next question, you also have to answer whether it is true or false. So options are A option true and false. Now I make the statement. The statement is double sideband suppressed carrier modulation scheme is the least bandwidth efficient among double sideband suppressed carrier, single sideband suppressed carrier, and vestigial sideband suppressed carrier modulations. So obviously DSB-SC is the least bandwidth efficient. The reason is it is taking the both the sidebands, the LSB, write it clearly, LSB plus upper sideband, both the sidebands they are taking. However, in VSB we take one of the LSB and some more part, whereas in SSB we just take either LSB or the USB. This is also same. In VSB we do not take LSB plus USB. A part of that is getting taken. So basically, this is the least efficient in terms of bandwidth. So the option is true. And also you can think it as like the DSBSC. If you are taking a DSBSC, you can think that every sideband is contains some repetitive type of information. So that is also sort of bandwidth wastage, because but that is not the case for SSB or PSB. I think these are clear from the video lectures that Sir has been provided. So let us go to the next question. Question number 3 says, envelope detection has the advantage option A helps in carrier recovery, requires less transmission bandwidth, requires less transmission power, eliminates the necessity of carrier recovery. So what we do in this sort of envelope detection is let me draw the circuit for envelope detection. So basically a signal is coming here. So let me draw the detector circuit first for the envelope detection. It takes a diode and then it is connected through the demodulation scheme, that is detector, right? So basically I'm drawing that, and another load is here, and the output is here. This is input is coming here, and I'm getting the output voltage here. So I can say this is the V in and this is V out. Basically, if there is a carrier frequency is coming here like this, what will the diode will do? Like this, at first this peak frequency, when this is positive voltage, only then this diode will pass, let it pass. So basically it goes here, and then this capacitor is getting charged here. So when the capacitor is getting charged slowly, and then it just taking the peaks, and then slowly it is again discharging. So it actually finding out the message signal here that is encoded in this carrier frequency. Similarly, if I think a carrier is a high frequency carrier, this means a high frequency carrier. Another carrier I can take it like I previously drawn. So both of them are modulating the same sort of signal. Okay. So basically it does not depend on the what is the carrier frequency here. It does not, according to the question, it eliminates the necessity of carrier recovery and requires less transmission bandwidth. Is it's a modulation scheme, not it cannot be done in the detector section, and requires less transmission power. That also depends on the environment, what is the noise power and all these things, and it does not help in carrier recovery. We have seen we are not detecting what is the carrier frequency, we are just taking the demodulated signal. So that is the reason the envelope detection has the advantage that it eliminates the necessity of carrier recovery. Okay, I think it's fine. So let us move to the next question. Says for voice communications, SSPSC modulation can be used for which of the following reasons? It requires less power, B, helps in synchronization, low frequency component of the voice signal is 0, bandwidth of the voice signal is small. So the correct option is here option C. This is because of the fact that this suppressed carrier SSPSC only taking one sideband, and the voice signal is 0 for very low frequency components. Like we do not talk in 0 hertz, nearly 0 hertz, 2 hertz. Our frequency starts from 300 sort of thing. So the very low frequency components of the voice signal is 0. That specifically helps the SSPSC modulation that only takes the either the upper sideband or the lower sideband and with the suppression of the carrier frequency. So the right option is low frequency component of the voice signal is 0. That is the reason that SSPSC can be used for voice communications. Now let us move to the fifth question. So fifth question is, we have a signal m of t that is sine of omega 1t sine of omega 2t and with the condition omega 1 is greater than omega 2, we have to find what is the Hilbert transform of mt, that is mht. We have to find mht, that is the Hilbert transform of mt. So we know what is mt here. Mt is sine of omega 1t sine of omega 2t, and then we write it in the form of cos a minus cos b. Cos of omega 1 minus omega 2 t minus cos of omega 1 plus omega 2 t. Now what this Hilbert transform means? Hilbert transform means it changes the phase of the signal by minus pi by 2. So it is easy to directly implement the phase shift of pi by 2 in this signal mt. What will be the result here is half of this cos will change to sine, as I am shifting by minus pi by 2. So this basically comes as omega 1 minus omega 2 t and also this cos will also be sine similarly of omega 1 plus omega 2 into t. So again, this is sin A minus sin B. And I can write this equation as follows. Sin of omega 2t cos of omega 1t. That is a trigonometric formula that we can use. Okay. Now let us go to the question number 6. It says a single sideband signal single sideband signal that is generated a modulating signal of 900 kilohertz carrier. And what is the MT here? Cos of 2000 pi t plus 2 sin 2000 pi t. And AC, that is amplitude of the carrier frequency, right? So we have to find out what is the upper sideband of SSB AM signal. So the single sideband is given by this. So basically this is the signal for given here, and a single sideband signal can be generated by modulating signal 900 kHz. So the single sideband signal you can generate from this. That is the thing. So the message signal is given, actual baseband signal, and the carrier frequency is given here. That is the clue here. MT is given here. Said what is the carrier frequency, carrier amplitude is given here, and it also said that a single sideband signal is generated by this modulating signal carrier signal and this MT. Both of them has generated this single sideband signal. So we have to find out what is the upper sideband USB of the. Okay, solve it. So it's the Hilbert transform of the signal sine 2 pi fct, right? This is the known formula for the LSB. Now the Hilbert transform of the signal is, so let me write what is MT. MT is cos 2000 pi t plus 2 sine 2000 pi t. So from this, the Hilbert transform of this signal can be written as phase shift of minus pi by 2. This is 2000 pi t 2 cos 2000 pi t. So we know what is MT, we also know what is MH of t. So MT we know what is MHT, we know what is FC. FC is 100 kilohertz here. So AC is also known, is 100. So just put all this information in this equation. It will be like equal to AC is equal to 100 and this MT is cos 2000 pi t plus 2 sine 2000 pi t into cos 2 pi fct. Not writing what is the fc. Fc is here 900 kilohertz. So that is 2 pi fc is equal to 900 kilohertz minus mh of t here. What is the mh of t is given here. So can be written as sine of 2000 pi t minus 2 cos 2000 pi t into 5ct. If I simplify these two equations, the whole term, if I simplify formulas, it will come like 100 cos 2 pi fc plus 1000 t plus 200 sine 2 pi fc plus 1000 t. So let me write the answer here. The simplified answer of x USB or LSB is 100 cos 2 pi fc plus 1000 t plus 200 sine 2 pi fc plus 1000 t. And fc is here like 900 kilohertz. I think this is clear for this. So every time you have to calculate some Hilbert transform, you have some cos. You just shift the signal by minus pi by 2, you will get the mh of t, and from there LSB and USB can be calculated from these equations. Okay. So now let us go to the next question. The question 7 says, if a message signal that is MT with a bandwidth B is modulated with a carrier frequency Fc, given the fact that Fc, this carrier frequency, is very large than the bandwidth of the message signal. Okay, so to form a VSB signal, vestigial sideband signal, this message signal MT is passed through a high pass filter. So pass through a high pass filter, so it will get suppress some low frequency components here. That's the way they are generating the VSB signal. And this filter has some characteristics. Filter has gain 1 and it has low alpha. So let me draw the picture for it. It will get more clear to you. So this is the carrier frequency. Here it is FC, and there is a sharp filter response like this. And then it is a high pass gain 1. And here it is, suppose it starts the roller factor here and it becomes 0 here. Okay. So it is the carrier frequency is in the middle, like here probably this is epsilon, and within a range fc minus delta f, it becomes the gain of the filter intensity. And here at fc plus delta f, linear frequency, linear type of slope here, it becomes the gain of the filter is 1. And then as it is a high pass filter, for all the high frequency components it has the gain of 1. So basically it will chop up the it will slowly, it will just, the gain will not be 1 for low frequency components, but for high frequency components the gain will be 1 at fc plus delta f from, and fc is the carrier frequency, and this is the slope is alpha. So we have to find out what is the excess bandwidth. The excess bandwidth is del f. So from the picture, it's very clear we can see that the slope alpha is equal to 1 by 2 del f from my this whole range is 2 del f. So 1 minus 0, and you can find the linear equation like from the linear equations you can find that this is the slope alpha. It becomes 1 here, value 1, here the value is 0, and this is fc plus delta f minus delta f. So the equation of slope is y2 minus y1 by x2 minus x1. This is the equation for the slope. You can find that alpha is equal to 1 by 2 delta f. From here you can find the excess bandwidth delta f is 1 by 2 alpha. So we need to find out what was alpha, and alpha should be depends actually slope is sorry, we are not find out like we have to find out what was delta f here, the excess bandwidth. What is the excess bandwidth for the PSBC? This is the excess bandwidth delta f because the carrier frequency is fc and it becomes 0 at fc minus delta f. So this is the part that is the excess bandwidth here for the PSB signal. And we need to find out what is the excess bandwidth relationship with this slope factor alpha of the high pass filter. So this excess bandwidth delta f has a relationship with the slope of the high pass filter, that is 1 by 2 alpha. So this was some sort of demo how we can calculate the relationship of a filter, slope of the filter with the excess bandwidth, and this alpha is sometimes called the Taylor factor. So basically we are finding how much the slope of, because you cannot get a sharp filter, right? Any filter you design, it will not be a sharp filter. So for this region here it is a slope type of thing. This can also be like this sort of filter, and this is then it is a high pass filter. This can also happen. So this is sort of example. Questions will be oriented about this sort of questions. I think it is clear with everyone. Let us go to the next question. Suppose there are 15 signals and each of them is band limited to 10 kilohertz. And all of these signals are need to be transmitted. All these signals should be transmitted over a single channel by frequency division multiplication. That is FDM modulation we are using here. So there are 15 signals, each of them is band limited to 10 kilohertz, and all of these signals should go through a single channel by only frequency division multiplexing. So now, if a single sideband suppressed carrier modulation is being used with a guard band is of 2 kilohertz, then what is the bandwidth of the multiplexer? Question is, what is the bandwidth of the multiplex signal? So I'm just repeating the question once again. We have 15 different signals and each of them are band limited to 10 kilohertz. Okay, so now we transmit all the signals over the channel with frequency division multiplexing. So for at different frequency we are sending all of them, and for this modulation we are using a single sideband suppressed carrier. Each of them has a guard band of 2 kilohertz. So there is a separation between them of 2 kilohertz between each of the signals using frequency division multiplexing. So the question is, what is the total bandwidth of the multiplex signal? The required bandwidth is 15 into 10. This is at least necessary for sending all these 15 signals of 10 kilohertz. Total bandwidth here is 15 into 10. That is 150. But there is also there are single sideband suppressed carrier, and there is a guard band of 2 kilohertz. For such, we will need another 14 because there are total number of 15 signals, so there will be 14 intervals in between them, and we are using SSBS. So the total bandwidth need is 164. 164 kilohertz.
So I have a question here. 14 guard bands of with 2 kilohertz each.
Yes, but
So it
you
will
are
be
using
14 into
SSBSC here,
2,
right?
right?
A single
Okay,
sideband you are
okay.
using.
So it's single sideband, so into 1 kilohertz. Okay,
Yes.
okay, sir. Thank you. Thank you.
Okay. So there will be two more questions just after 2 minute break. Okay. Let us move to the question number 9. So the question number 9 says, consider a baseband signal. This baseband signal has a maximum frequency 0.3 kilohertz sorry, the maximum frequency is 0.4 kilohertz and the minimum frequency is 0.3 kilohertz. So we have a baseband signal, and this baseband signal has a maximum frequency of 0.4 kilohertz and minimum frequency is 0.3 kilohertz. So this signal is modulated with a center frequency ten kilohertz. Now, if we want to make a lower sideband SSP signal from this baseband signal, what should be the minimum and maximum bandwidths of the filter? What is the minimum and maximum bandwidth of the filter? Or the question is not about what can be the minimum, what can be. It is better that if I write what can be. So I am repeating the question once. We have a baseband signal, and this particular baseband signal has a maximum frequency of 0.4 kilohertz and minimum frequency of 0.3 kilohertz. And then this signal is getting modulated with a carrier frequency that transfer the sequence to a center frequency of 10 kilohertz. Then we want to find a LSB lower sideband of SSB signals, single sideband carriers, single sideband carrier signal from this baseband signal. For this reason, we have to use a filter, and I'm asking what can be the minimum and maximum bandwidth of the filter so that it can generate a LSB SSB signal from this baseband created by this baseband signal and this center frequency carrier signal. So the carrier signal has a frequency of 10 kilohertz, baseband signal has a bandwidth of 0.1 kilohertz. You can see from 0.4 to 0.3 kilohertz actually. So what should be the minimum or maximum bandwidth that will not hamper the signal creating the LSB SSB signal? That is my question. Okay. So what should be the minimum bandwidth? So minimum bandwidth, you can think that this signal has a bandwidth of 0.4 to 0.3, right? So basically this is the signal. This is 0.3, this 0.4, minus 0.3, 0.4. This is the baseband signal. So if I want to create a LSB SSB signal, it at least should have a frequency of 0.4 minus 0.3, that is 0.1 kilohertz. Now if I modulate this signal by a frequency of 10 kilohertz, this too will get repeated here and here, with this is 10. So here this is 10.3. So the maximum filter response to only catch the LSB part here, it should not cross this 10.3, right? So the maximum bandwidth that can be is 10.3 kilohertz, so that it only captures this part. If it becomes greater than 10.3, it will start to capture the upper sideband part also. So the minimum is 0.1. So 0.1 is like this. The maximum is 10.3. Kilohertz. Okay. Now move to the last question of today's session. So this says, the question is more of same. The question says that now we are modulating by a carrier of 2.3 kilohertz instead of 10 kilohertz. And again we are forming a LSB SSB signal. So now we are again forming a LSB SSB signal, but this time with a filter. Again we have to consider that slope type of information. So this time the carrier frequency is 2.3 kilohertz. 2.3 kilohertz FC. Now we are generating a LSB SSB with help of a filter. Again, this filter has a maximum gain of 1, And again, that roll-up factor alpha that we have described earlier. So basically it has a gain of 1 and roll-up factor of alpha. Now the point here is we are using the band 0 to 1.6 kilohertz for another communication. Okay, so we have to find out what is the value of alpha. So basically the picture diagram will be more easy to understand. So again the signal becomes like this. After modulation, obviously it was, this message signal was like this, and then we do a modulation with 2.3 kilohertz center frequency, and we are getting this sort of spectrum. But there is a constraint. We are saying that the band 0 to 1.6 kilohertz, we cannot transmit any part of this signal because we are using this band for communication of another signal. So this band 0, if it is 0 to 1.6, cannot be used for this communication purpose. Otherwise it will create some interference with that particular signal. So for that reason we have to use a filter alpha with roll-off factor alpha, so that in this region this filter response is like this. There is no interference of this particular signal goes in this region. So what should be the slope of alpha such that it becomes the gain of the, so the question is more of the gain of the filter should be 0 at 1.6 kilohertz, right? Because if the gain of the filter is not 0 at 1.6 kilohertz, then if this signal has some part that is crossing 1.6 kilohertz, that will create interference in this region. Like if this signal stretches out like this, then if the gain is not 0 of this filter, then this part will create interference with the signal that is within 0 to 1.6 kilohertz. So basically we are trying to avoid this kind of situation, so that we are using one filter here, and that filter will just cut off that part. Okay, so what will be the value of alpha? That is the question. And also this filter should not sample any part of this signal also. That is also the reason of creating this filter. Like if this filter is getting in this region, then it will take the sample of this signal, and it will be counted that this DSP SC signal has a part in this region. So basically we have to avoid this filtering process such that it does not cross this 1.6 kilohertz, so that these two signals does not interfere with each other with the help of the filter. So that we have to find out. That is the reason why we are using this sort of linear roll-off factor. So I think it is clear, like if this signal goes, it is this filter response goes like this, then the signal in this part will also be treated as the part of this signal, and that is not the case for our scenario. Our signal is limited to this region only, not in this region. So that is the reason we should use a cutoff filter, so that it only takes this region of the frequency response. And for this, what should be the alpha? Okay, so let us solve this question. So we had a signal that was from like this, minus 0.3, minus 0.4, 0.3, 0.4, and then we just transformed it at 2.3 kilohertz. So signal becomes like this. So this will be, this part will be 2.3 minus this 0.4. That is equal to 1.9 kilohertz. So that is the region where our signal ends. And another signal has the maximum frequency of 1.6 kilohertz. So at 1.9 kilohertz, the linear filter should have a gain of 1. And at 1.6 kilohertz, the gain should be 0. That is the equation we have to find. So y at 1.6 equal to 0, y at 1.9 should be 1. Right? So from this we can find alpha is equal to y of 1.9 minus y of 1. Sorry, this will be better if I write another equation. So from this, alpha should be y 1.9 minus y 1.6 by 1.9 minus 1.6. So what is the value of y 1.9? Our condition says at y equal to 1.9, this 1.9, it should have a value of 1. 1.6, at 1.6 it is 0, at 1.9 it is 1. Y 1.9, this is at y 1.6. So condition is this should be 1 is 0 by 1.9 minus 1.6. This is 3.33 hertz inverse. So the roll-off factor alpha should be calculated like this. Okay, I am displaying question number once again. So question number one says, question number one was, it was a simple statement question. Question number one said that we have two defined questions, the two defined modulation schemes, SSBSC and VSBSC. And we had to comment true or false there. Statement was both these modulation schemes are used for video and voice communication. And you have to comment whether it is true or false. So we know SSBSC signal, it is suppressed carrier. So this can be used for voice purpose, because there is low components of our voice signals that is not important for communication. So it is efficient for communicating with to perform voice communication. But in terms of video communication that may have zero frequency components, it will be difficult to do communication with SSBSC modulation. So basically the statement is false, both of them cannot be used. Only VSBSC can be used for both video and voice communication. Okay. So anybody has any doubt for today's session? Okay, then we will meet in the next Sunday.